Thanks, guys. Hi, I'm Shubham. I'm a software engineer with Bloomberg, and I work on Spark for online analytics. So we'll start this talk by discussing exactly what Bloomberg is all about, how data and analytics fit into what Bloomberg does. We'll talk about what the role of Spark is in, filling up some gaps in that picture. We'll then talk about what we call the Bloomberg Spark server. And finally, we'll discuss how we can actually start using Spark for some online use cases as well. So let's get started. Data and analytics are at the core of Bloomberg's business. Bloomberg has what's called a Bloomberg terminal, and this is a one-stop shop for all kinds of financial data. If you're in the financial world and taking roles, and your role involves making decisions on finances, chances are you would be using the Bloomberg terminal. You could be a trader, you could be a portfolio manager, you could be a CEO, you could be investment banker or anything of that sort. You would depend on, in some way, shape, or form, on a Bloomberg terminal. And the kinds of data we have there is, it spans the spectrum. A lot of you might have heard of news. This is some of the other kinds of data we have. We have geospatial data, we have time series, we have analytics that are enriched from raw data that we get about companies, right? So the kinds of data sets span the spectrum. They come with different frequencies, they come with different sizes, they come with different kinds of expectations. So to sum it all up, a lot of the analytics require really fast responses, and very often the consumers tend to be human. So we speak about being real time, but human time, real time, so to say. We definitely want to be scalable in that we want to be able to serve more users, a more complex suite of analytics on wider data sets. And as I showed you, we have a lot of different kinds of data that resides in a lot of different heterogeneous stores. These are stores like open source stores like HBase and Solar. There are some other internal stores as well that we have organically developed. Given that everything is finance here, we want to be able to present the latest, greatest, and the freshest data and analytics based on the latest data to our users, because our users kind of depend on us for that. Now, with all of this and the terminal, which itself is a premium product, there's a very high expectation of the quality of data we present, the kind of analytics we present, and the reliability of the system. So how does Spark fit into all of this, all the analytics, and especially online analytics? Spark itself is a framework that distributes, that gives us capability to distribute computing. Very often you come across problems where if you want faster results, you more often than not want to be able to just throw more machines at the problem and be done with it. Spark gives you that flexibility. Spark also has, with version 2.0 and later, the notion of data sources that allow you to connect to multiple disparate data sources without having to worry about the nitty-gritties of, how do you write a HBase query versus how do you write a Solar query, right? And then treat all of these data sets almost uniformly and be able to perform even cross-asset analytics if you want to. So data sources in some way do away with the idiosyncrasies of specific data stores, and you as a developer don't have to worry about that. Apart from this, Spark also has connectors and primitives that deal with stream processing, which plays a very big role in the kind of work that we are interested in, because that helps us ingest real-time data, real-time financial data. And in some cases where you want really fast responses, Spark also lets you cache intermediate query results. So all of these make Spark a pretty good fit for the kind of analytics that Bloomberg's interested in. So of course, a lot of applications inside Bloomberg were interested in Spark, and we ended up with something that looks like the image on the top there. You had a specific application, coming up with its own Spark cluster, using its own data store, right? And then deploying that Spark application. Now, as you can probably tell, there's a lot of redundancy here in the way applications are accessing and managing their data, managing their RDDs or data frames. And very often you would have the same kind of transforms being expressed over and over again. Not to mention, managing the clusters themselves, which isn't a very easy thing to do. And this also results in a kind of siloing where analytics can be confined to specific asset classes, making cross-asset queries not only hard, in a lot of cases, almost impossible. And each application would then also come up with their idiosyncratic solutions to handle real-time data ingestion. So what we actually wanted was to get to a point, get to a framework that looked something like the image below, where you have a single Spark cluster, and you have multiple applications deployed on it. And that was more or less the genesis of Bloomberg Spark Server. So this was basically a single long-running Spark application. The applications you wanted to run on it would be deployed as what we call request processors. And the application itself would open up a REST API that you can use to interact with the request processor. Now, this application could be deployed on Yarn or Mesos, or if you have a new resource manager tomorrow, maybe even that. Given the nature of the analytics we want, we make a very clear distinction between ingest time transforms and query time transforms. For us, because we want real-time and interactive applications, ingest time transforms are something we look at as things that help us load and in some way make data available in a hot cache. So when a Bloomberg Spark server comes up, all the applications that are registered with it would have loaded the data that they depend on and cached it in the Spark cluster. That for us is an ingest time transform. The query time transform, on the other hand, is something that comes in via, that is parameterized and comes in via the REST API. So the queries are pre-baked in your request processors. You get all the parameters you need from your REST endpoint, and then you execute those queries. So putting all of that together, this is the kind of image you get. So you have a request handler which knows all the request processors that are deployed as a part of this Spark server, and it takes in HTTP requests and routes them to the corresponding request processor. Underneath, you have a single Spark context that is holding on to an entire Spark cluster. So the request processors themselves can depend on data sets, and these data sets are maintained in what we call the MDF registry. These data sets are something that the request processors at the time of registration let the Spark server know about. So when we bootstrap and bring up Spark server, these data sets are loaded in the cluster and are made available for the request processors. There's another important piece there called the ingestion manager, and this is what takes care of the ingest time transforms and makes sure that the data is constantly refreshed. And you can have several ways of doing that, and then I'll go into some of this. So as I spoke about the ingestion manager, the data access itself tends to have long tail characteristics in that very often, it's only the 20% of the data that accounts for, say, 80% of the queries you are running. And this leads very well into scenarios where, you can subset a small portion of the data and then cache just that portion and still be able to get pretty good query performance using that. So the ingestion manager actually allows for you to express this kind of subsetting as a filter predicate, which you can specify at the time of registering the request processor, and it will take into account this filter predicate while constantly refreshing the data set. Spark itself offers all the primitives you need to unify this cached data set along with the backing store. So if your query, as a user, you want to express a query, you can be sure that, if a query needs more data to be fetched, Spark can transparently do that behind the scenes for you. All of the caching sounds pretty good. How reliable is it, right? So let's look into that. Spark itself has the notion of RDDs, resilient distributed data sets. The resiliency comes from the execution lineage being available in the driver. Now, if you have a cached RDD and you lose certain blocks in that RDD, the execution lineage from the driver is replayed to generate those RDDs, right? So how does the driver do that? This thing actually happens when your query executes. So this will definitely have a significant performance hit on the queries you're running if you lose data that you have cached previously. RDDs themselves offer various modes that you can use to get around this problem. So some of you might have used the memory-only 2 or memory-only serialized 2 modes. This basically creates 2 replicas of the RDD in your executors. So this helps you, get around RDD loss scenarios, and it's also easily extensible even beyond this. The Spark core actually allows for it. Apart from this, Spark also allows for speculative execution, which is where you might have executors that are running really slow. It's a fairly tunable execution model where you can actually find out if certain executors are really slow, and you can maybe fire speculative queries and have that same job run on a different executor. Apart from this, from Spark 2.0 and later, a lot of effort has been put into putting data off heap, and this has a pretty good performance impact. It improves the performance a lot by minimizing GC stalls and garbage collection delays. So this still leaves some gaps, and we'll soon talk about the gaps. But for us to be able to understand that properly, let's quickly look at what Spark actually looks like right now. So as we all know, Spark has a driver, and executors. have shown 2 executors here, just for example. Now, when you create an RDD, what actually happens is you just have the references of an RDD maintained in the driver. Now, this RDD reference actually has pointers to where RDD blocks might be stored on different executors. And the entire structure is stored using what Spark calls block managers. So for example, in this case, I've shown an RDD that has 2 partitions, and those partitions reside on executor 1 and 2 in the block managers. Now, within the block managers, each partition is mapped to what's called a block. For the purposes of RDDs and this discussion, it's actually a one-to-one mapping between an RDD block and an RDD partition. All the communication between the driver and executors happens using an RPC layer that's controlled by block manager master on the executor side and the master endpoint on the driver side. So let's say you fire a job and you ask for an RDD to be cached. What happens is the driver sends a compute request to the executor, right? The executor is the one that actually does the crunching for you and generates the data, right? And once that data is generated, it asks the driver to give it the list of its peers. And driver responds to that request by listing all the executors that are still alive and connected to the driver. On these executors, the executor then, from these executors, it picks up one executor at random and then sends it the block of data. And once that block has been saved on the other executor, this is the memory only two caching mode, let's say. And once the block is saved on the other executor, only then the result of the computation is sent by the first executor. So this is the reason whenever you cache something, you should probably run some operation on it, like say a count, if you want the data to be actually loaded, because otherwise the data would only be loaded when you run your queries. So now that we understand replication and Spark driver internals to some extent, what are the challenges in block replication, right? So we already saw how lost RDD partitions are generated at query time. And if you only have a single partition, then losing that partition would really have a bad impact on your query performance, and that data would be replenished at query time, which you definitely don't want. So you go with multiply replicated RDDs, right? Do they solve the problem? Well, RDDs are replicated at random by Spark. So if you, let's say, use a resource manager like Yarn, which is the case in Bloomberg generally, on Yarn, you can actually have multiple executors on the same node. And this basically means that you can actually have multiple copies of the data on the same node, and you now become susceptible to node failure. So even if you have, say, 2 or 3 replicas of the data, they might end up on the same node. You lose the node, your query performance just goes through the, delays go through the roof. What's more, if, let's say, you have executor losses and you lose certain blocks, Spark doesn't replenish these blocks proactively, which means, especially for long-running applications like the one we are talking about here, your application might lose blocks while it runs, and these blocks would not be replenished by Spark. It will only try to replenish them once you lose all the blocks, which would again be pretty bad for query performance. To answer some of these challenges, we started working on a few JIRAs. This one, for example, Spark 15352. This is an umbrella JIRA, and as a part of this, we made peer selection pluggable. And the default implementation just replicates what we have in Spark right now, which is choose a random peer. We inject a topology mapper. This is something that the driver holds on to. The default implementation, again, is script-based and is very similar to what we have in HDFS, right? So the driver now decorates all executor with topology information. And when executors, like we saw earlier, an executor asks the driver for the list of its peers, right? The topology information is now annotated with the list of peers. So the executor can use that information and make a better call on where to place the blocks. We also put in a customized prioritization strategy. So for example, you could have a lot of different kinds of replication objectives. You could want one replica of the data being available in the same rack. You might want another replica available on a different rack, or you might want to express your replication objectives like you don't want more than 2 replicas on the same rack. So both affinity and non-affinity based replication objectives. We put in a constraint solver that looks at these objectives, and it tries to come up with the minimum number of peers that might be needed to satisfy all or most of the objectives. So we also did a lot of simulation studies on this constraint solver on as many as 100,000 nodes, and we found it to be quite stable and performant as well, and didn't really take a lot of time. Apart from this, we also contributed some code for proactive replenishment of lost replicas. This is to ensure we don't run into the problems we just discussed, where Spark waits for all the replicas to go away before it starts to decompute. In this case, whenever an executor is lost, the master recognizes that and then contacts all the peers that have that block and picks one peer to start replicating the block proactively. And I would really like to thank Reynold and Eric from the Spark community, who helped us a lot with feedback on all of this. That's still those are some of the so to say the low-hanging fruit of high availability that we try to address. There are still some challenges in Spark, specifically around the driver itself. Now, we all know if you lose the Spark driver, you lose all the executors, and all the cache state that went with the executor goes, that was there on executor goes away with it. So there's a very high bootstrap cost of reconstructing the cluster and the state. And we can come up with very naive HA models, like having fully fledged multiple clusters running simultaneously. And we'll soon discuss what might be the problems there. So all of this put together, because we actually want queries to be responded to in real time and in an online fashion, high availability for us is very it goes hand in hand with low latency. If you don't have availability, even if you're really slow in responding to queries, it doesn't quite work for us. And here we also want not just average latencies to be good. We actually also look at 95 to 99% latencies as well. One of the naive solutions, and this is something that we tried to go in production with, is where you actually have multiple full-fledged Spark server instances, right, all running together. They all synchronize and pick up and decide on a leader with the help of a zookeeper cluster. A client can only get a response from the leader, as shown here. If a client sends a request to a Spark cluster that is not the leader, the Spark cluster internally redirects that request to the leader, gets a response, and then responds back to the client. So what this ensures is there is no data inconsistency between the multiple Spark clusters. Now, if let's say you have some data cached, you cannot be sure that all three of them start caching the data at the same instance. So there could have been very minor data inconsistencies between the three, which you don't want surfaced to your queries. You cannot have two traders talking to each other, seeing different prices of something that one is trying to sell and the other is trying to buy. So to ensure consistency like that, we have to make sure that the data that goes into these analytics is consistent, and this is the way we ensure data consistency there. Now, all of these Spark servers internally have their own ingestion managers running, and then are getting constantly refreshed. And does this answer all the HA challenges we had? Not quite, because if we lose an RDD partition in the leader, we see exactly the same set of problems. RDD loss in the leader is still a big concern on the query performance we'd likely see. The performance in this case is also gated by the slowest executor we have in the leader. And if let's say the leader is getting overwhelmed by a large number of requests, the other Spark servers which are non-leaders, they're also constantly refreshing, but they aren't really helping with the query workload at all, right? So that's the reason we call this more of a storm and not really a workable solution. So we spoke a lot about the driver and the problems around high availability that the driver has. What exactly is the Spark driver? At the very core of it, it is basically just a Java application, right? It maintains a lot of state, what kind of jobs you ran, how long they took, how many executors are connected. Some of the state is interesting, some of the state is really hard to regenerate, while there's a lot of state that's not so interesting and might be done away with. So for online use case specifically of these kinds, what we are interested in are basically just the way RDDs and data frames are created, specifically the ingest transforms. Now, with data frames, you have the notion of logical plans that went behind creation of the data. And these logical plans give you something like a signature to denote that data, right? And that makes a very clear separation between the plan that went into creating the data versus the data itself. Comparing that to RDDs, this plan is basically just Java bytecode, right? And that becomes a lot harder to deal with. So apart from this state, there's some other state in the driver, like which blocks are present on which executors. That is really interesting, right? The cache manager, in case of data sets and data frames, holds on to the mapping between logical plans and data frames, and any subsequent queries that might use that data are short-circuited using this. We also have a job scheduler that keeps a track of what the different stages are, what tasks are running, and basic executor information. Now, all of this state is not fully exhaustive. There's a lot more state in Spark driver. Now, what if some of this state could be externalized, right? If we were to externalize some of this state, we would see that we will likely have a lot quicker recoveries, because we can now have multiple drivers that can, at a moment's notice, read this externalized state and pick up from where the previous one left. Executors don't have to be lost. They can actually still persist. There can be some other driver they can now start talking to. And we can even potentially talk about active drivers at this point. Those actually look like pretty good benefits. How do we even go about solving some of these problems, and what kind of solutions might give us those benefits, right? One of them is using off-heap storage for RDDs. This would be a system like, say, Tachyon, which can store all the RDDs you have, right? Now, even if you lose the driver and your executors, you can have the whole thing come up again and just read the data again from Tachyon, and that would solve your problem. And whatever residual state you have, you can put into something like, say, Zookeeper. Just to be clear, this is just the residual state you're putting into Zookeeper, not the data. What you end up with is something of this sort, where you have a pool of executors that all speak with multiple drivers. Now, this residual state is stored in the form of the job scheduler and cache manager. If, let's say, a query comes in, specifically the ingest transform that we talked about, and it, let's say, comes to driver 2, driver 2 can trigger the job, have the results cached, and like we saw earlier, where the executor tells the driver what kind of blocks it has, nothing really stops the executor from telling multiple drivers what kind of blocks it has. So the executor can actually simultaneously send that information to multiple drivers and have both the drivers available in an active standby kind of configuration. In summary, we saw that Spark as a system for online usage does have some gaps, but with some architectural modifications, with the help of community, of course, these gaps can actually be overcome, and Spark can actually fill in the role of an online system as well that can respond to queries in real time. Apart from this, the architectural changes that might be needed may not be as invasive, and Spark can clearly play the role of an online query system as well. I would just like to thank Reynold and Eric for their feedback, and yeah, thanks.
Thank you. I'm afraid we don't have any time to take any questions, but Shubham is going to be walking around, so you can probably escort him outside and ask him whatever you want. But thanks a lot for all your work, for making sure that the Spark community benefits from all the work you're doing at Bloomberg and all the PR requests you guys have done. And thanks for acknowledging Reynold and Eric of Databricks. Thank you.